Hello everyone, I'm Yuhao from University of California, Riverside. Today I will present our paper, Demystify the Dependency Challenge in Kernel Fuzzing. First, I will give some background about kernel fuzzing, the state-of-the-art kernel fuzzer syscaller, and how syscaller works. Linux kernel is widely used in servers. For example, there are many different Linux distributions. And the cell phones, for example the Android. Fuzzing has become one of the most popular and essential methods for uncovering bugs and vulnerabilities. Zscaler, which is the state-of-the-art kernel fuzzer, has found or fixed more than 4,700 bugs in Linux kernel. First, Zscaler generates template from Linux kernel by human. The template, which is knowledge about the syscalls, includes the name of syscalls, for example the open and L control here, the arguments of system calls, for example the fd, command value and arguments of the L control, and the dependency between them, which is the return value of open could use as the first argument of L control. Syscaller could generate valid test cases from those templates and execute them in the Linux kernel. Then Syscaller pick interesting test cases by new coverage. From those interesting test cases, Syscaller could mutate them based on the template to get more test cases. This is the workflow of Syscaller. By the way, template is called syscall description now, and you can find more details in the link below. Then we will talk about motivation of this paper, dependency challenge, and we will give one example case and some definition to help understand the whole paper. We have efficient fuzzing algorithm in syscaller. We have sufficiently long fuzzing time. There are also comprehensive templates for some kernel modules. However, all of them can only achieve a coverage of 48%. What else prevents syscaller to get more coverage? The answer is dependency challenge. This paper wants to figure out the root cause behind the dependency challenge in kernel fuzzing. Look at this example. The conditional at line 1 has one uncovered branch, so it belongs to unresolved condition. Since it reads value from some global memory, which is field cdda underscore method in CDI here, it also belongs to unresolved dependency. The code at line 6 writes value to the field cdda underscore method in CDI, so it is a white statement for the unresolved dependency at line 1, because it can change the global memory to an expected value. It is also the effective white statement for the unresolved dependency at line 1. And we define the dependency is the relationship between the unresolved dependency and its effective white statement. Notice that the dependency in Linux kernel are similar to the diffuse in the user space program, but the dependency is specific to global memory and the use has to be a conditional check. The unresolved dependency and the white statement could be in different entry functions, for example different syscalls, or even not in syscalls at all. Now we will introduce our measurement pipeline. For given kernel modules, we first run fuzzing to collect coverage and unresolved conditions. There are 4,700 goal lines of changes based on syscaller for collecting statistics and data sharing. Then we use static intent analysis to determine unresolved dependency and recognizing their white statement, which has 4,000 C++ lines of changes based on Dr. Checker. After getting white statements, we have to manually figure out the effective white statement, whether they are influenced by other unresolved dependency, and the root causes behind them. Notice that Because the coverage is based on binary and the static analysis is based on LVM, we have another mapping component with 6,700 C++ lines of code and 500 protobuf lines of code for mapping between binary and LVM bitcode, organizing information to support manual analysis and data sharing. Then we will show some measurement results to show how prevalence of unresolved dependency and the challenges to get root causes. On average, we found that 62% of edges are uncovered edges, and 75% of unresolved conditions belong to unresolved dependency, which means the dependency challenge is a major issue for those uncovered edges. If we consider the dominant edges of unresolved dependency takes 73% of all dominant edges of unresolved conditions. For each unresolved dependency, there are about 13 white statements on average. About 67% of white value are expressions instead of constants, which means that it is difficult to identify effective white statement by static analysis. Based on our manual analysis, the number of effective white statements is far smaller than the number of white statements, often only one. Another challenge is recursive dependency. For example, the unresolved dependency at line 1. Its effective white statement is at line 5. However, in order to reach the effective white statement at line 5, we have to satisfy another unresolved dependency at line 3 first. About 35% of white statements are uncovered, and most of those uncovered white statements are recursive dependency. Although syscaller has some mechanism, the test cases generated by syscaller are unstable, which is we have a test case and get its coverage. If we execute the same test case later, the coverage would be different. We found for the test cases that were previously able to reach the unresolved dependency and white statement, a large number of them become unstable. Now we will present the root cause of those unresolved dependency. We pick 4 different types of kernel module, run a long fuzzing on them, and sample more than 100 unresolved dependency. After more than 300 human hours, we finally find 5 root causes and their distributions. To our surprise, the biggest root cause is dead code, which is about 30%. Although dead code is a well-known issue, we guess that the reason why compiler fail to identify them is that they are related to global memory and need an inter-procedure analysis. For example, the code at line 3 would delete all client in the global array queen_list by the client number. However, the code at line 4 would check all client in the same global array by the same client number. So the unresolved dependency at line 8 would never be satisfied. The second biggest reason is environment dependency, which is about 23%. The environment for the Linux kernel is mainly the hardware. For example, in order to satisfy the unresolved dependency at line 1, we have to reach the effective white statement at line 9. However, we found that if there is one IDE CD-ROM, we would always reach the white statement at line 6. Only there is a GD-ROM, we can reach the effective white statement and satisfy the unresolved dependency. Another interesting root cause is the unobserved dependency, which is about 10%. Besides the system calls, there are some functions can be triggered by other interfaces of the Linux kernel. For example, bottom half position, module init and exit functions, callback functions, interrupt. For example, the unresolved dependency at line 1. If we trigger this function from system call IO control, we can never satisfy the unresolved dependency. Only the module init function could satisfy the unresolved dependency. The next root cause is incomplete template, which is about 19%. Although we have already picked the kernel module with comprehensive template, we still find that some unresolved dependency are because of incomplete template. For example, miss argument value, miss explicit dependency. And we also find some other issue in other template. For example, wrong argument type, miss return value of system calls, or even miss command value of IO control. Here we give you one example from KVM. The argument at line 2 of IO control at line 1 sets some global memories, and the IO control at line 4 uses the global memory in the unresolved dependency at line 9. In order to satisfy this unresolved dependency, we have to set a suitable value in the memory address at line 7. The last root cause is specialized search requirement, which is about 8%. There are two kinds of situations. One is the interleavings of multiple threads. Another is a special sequence of this call. There may be code like ++i inside these calls, so it needs to repeat the syscall many times. Then we will introduce some interesting future research directions from those root causes. The first one is multi-interface fuzzing. As we mentioned, there are a lot of different interfaces of Linux kernel besides the syscalls. We need to combine them together to generate test cases of fuzzing in order to achieve a better coverage. The second is syscalls input propagation analysis. For some complex syscalls, it may set some global memory by user input at one syscall, for example the syscall 1 in the figure. Then use the global memory at other syscall, for example the syscalls 2 and the syscall 3 in the figure. And there are some complex calculations, for example the function 1, function 2, and function 3 in the figure. If we can analyze all those constraints, we can generate a more complete template for the kernel fuzzing. Then we will give the conclusion of our paper. Overall, we conduct an in-depth investigation of the dependency challenge in kernel fuzzing using a combination of static and manual analysis. We demonstrate the challenges when analyzing the unresolved dependency in the Linux kernel. We distill the root causes of the unresolved dependency. Thanks everyone. That's all of our presentation.